Systems of linear equations. So first we're going to start with a 3x3 system, so a system of 3 equations with 3 variables, and verify the solution. When you're given an ordered pair, or in this case an ordered triple, which as the solution, you should assume that the values are written in alphabetical order. So 2 is our x value, -3 is our y value, and 1 is our z value. So what we need to do is verify this solution in all 3 equations. So let's start with the first equation. If I substitute my values in, I get 4 times 2 minus 1, and I'm checking to see if that equals 7. So 8 minus 1, which is 7. So this does check out in that first solution. So, sorry, the solution checks out in the first equation. Let's check it now in the second equation. So does 8 times 2 plus 5 times -3 minus 1, does that equal 0? So 16 minus 15 minus 1 equals 0. So yes, the solution checks out in the second equation. Let's finally check it out in the third equation. So the opposite of 2 minus -3 plus 5 times 1, does that equal 6? So you have -2 plus 3 plus 5, which does equal 6. So yes, the solution checks out in all 3 equations, so that means we have verified the solution in this system. It was not enough to check it in 1 or even 2 equations. We did need to check it in all 3. Okay, now let's look at actually solving a system of equations. And there are a variety of methods that we could use for these systems. So here we have a 2x2 system, a system of 2 equations with 2 variables. And we have 2x plus 4y equals 2/3, and 3x minus 5y equals -10. So here I'm going to use the process of elimination, and I'm going to choose to eliminate my x variable. So in order to do that, I need to multiply both equations by a number so that when I add the equations, the resulting equations together, my x's will cancel out. I will multiply the first equation by 3, so I'll have a 6x, and I will multiply the second equation by -2, so I'll have a -6x. So I choose to always add my resulting equations together. Yes, it's true you could subtract them, but I usually see students make a lot more mistakes when they subtract equations. So multiplying these equations, I first end up with 6x plus 12y equals 2, and multiplying my second equation, I end up with -6x plus 10y equals 20. When I add these together, my x's are eliminated. Good, that was what my plan was. And then I'll add my y's and then my constants. So 12y plus 10y equals 22y, and 2 plus 20 equals 22. Now I'll divide both sides by 22, and y equals 1. So now I have part of my solution. I have the y value. To get the x value, I need to substitute y equals 1 back into either one of my original equations. I'm going to choose to use the second equation, but you could just as easily use the first. So substituting in, I get 3x minus 5 times 1 equals -10, or 3x minus 5 equals -10. I'll add 5 to both sides, and then I'll divide both sides by 3, and x is -5/3. So I can either state my solution as x equals -5/3 and y equals 1, or I can write my solution as an ordered pair. -5/3, comma 1. Always alphabetical when you do that. Okay, let's look at another system, another 2x2 system. Here I have x minus y equals 5, and -3x plus 3y equals 2. So here I'm going to use substitution to show you an example where I use the another method. So I'm going to take my first equation, and I am going to solve it for x. I will get x by itself, and I'll do that by adding y to both sides, and x equals 5 plus y. Then I will substitute 5 plus y in for x in the other equation, in my second equation. So substituting in, I get -3 times 5 plus y in parentheses plus 3y equals 2. I'll distribute and get negative 15 minus 3y plus 3y equals 2. And my y's cancel out here, so I end up with negative 15 equals 2, which is a statement that is never true. So that means that this system has no solution. Or, in more math terms, it's inconsistent. So just to review those math terms, if I have no solution, a system is inconsistent. If I have at least one solution, that means I could also have an infinite number, then my system is consistent. And if I were to look at the graphs of my equations, so if I had a system, like on the previous slide, where my lines, if I graphed them, intersected in a point, that means I would have a consistent independent system. If I have two parallel lines, like I would if I graphed the two lines in on this slide, then I would have an inconsistent system. And if I ended up having two coinciding lines, I would have a consistent dependent system. So let's look at one more system of 2 by 2 equations, or one more 2 by 2 system. So here we have 2x minus y equals negative 1, and x plus 1/2 equals 3/2. So I'm going to choose to get rid of my fractions in my second equation by multiplying that equation by my LCD, which is 2. And that means I end up with 2x plus y equals 3. And if I leave my first equation the same, 2x minus y equals negative 1, I can see that I'm already set up to eliminate my y's if I add these equations together. So adding them, my y's eliminate, and adding my x's, I get 4x. If I add my constants, I get 2. Divide both sides by 4, I get x equals 2/4, or 1/2. So now I have half my solution, and I'm going to choose to substitute 1/2 in for x in my first equation, but you could also substitute it into the second equation. So 2 times 1/2 minus y equals negative 1, or 1 minus y equals negative 1. Subtracting y, we get the opposite of y equals negative 2. Dividing both sides by negative 1, y equals 2. So I can either write my solution as y equals 2 and x equals 1/2, or as the ordered pair 1/2 comma 2. Okay, so let's look at a larger system like we had on our first slide. So this is a 3 by 3 system, or a system of 3 equations with 3 variables. So I am going to, and I can use a variety of methods on this as well. I can use substitution, I can use elimination, I can use a combination. So I'm going to take my first equation, and I am actually going to solve it for y. I'm going to subtract 2x from both sides and get y equals negative 4 minus 2x. And then I'm going to solve negative 4 minus 2x in for y in my second equation. And if my third equation had a y term, I would substitute it in there as well. But in this case, it doesn't. So substituting into that second equation, I get negative 2 times negative 4 minus 2x plus 4z equals 0. Distributing, I get 8 plus 4x plus 4z equals 0. Going to subtract 8 from both sides and put this in standard form. So 4x plus 4z equals negative 8. And I'm actually noticing that all 4 of my terms have a common factor. I'm going to divide everything by 4 to make my numbers smaller. So I have x plus z equals negative 2. So this is an equation that we'll use momentarily with my third original equation. And I normally would have substituted y equals negative 4 minus 2x in for the y value in my third equation, but I didn't need to. So I could skip that step because there was no y term in that third equation. So bringing the third equation down, I have 3x minus 2z equals negative 11. And so now you see we have a system of 2 equations with 2 variables. I'm just trying to number as I go so you can keep track of each step that I'm kind of doing here. Because that is the biggest thing that students have trouble with 3x3 systems when you're doing them by hand, is keeping track of your work and staying organized. So for this 2x2 system, I am going to use elimination, and I am going to choose to eliminate my z's by multiplying my first equation by 2. So you could have chosen to eliminate your x's, you could have chosen to solve for a variable and use substitution. So here, multiplying my first equation by 2, I get 2x plus 2z equals -4. I left my second equation alone, so 3x minus 2z equals -11. So now when I add the two equations together, my z's cancel out, and I have 5x equals -15. Or dividing both sides by 5, x equals -3. Okay, so now I will take that and substitute it into that first resulting equation that I had when I solved for y, and this will help me determine my y value. So y equals -4 minus 2 times -3, or -4 plus 6, or y equals 2. So now I have my value of x, my value of y, and it doesn't matter what order I'm finding those in. I do still have to find my value for z. So I need an equation with z and one or both of my other variables. So I am going to choose to use the middle equation and solve for z. And I could have just as easily used my third. I could not use my first one because I did not have a z in it. So substituting into that middle equation, I have -2, substituting 2 in for y, so -2 times 2 plus 4z equals 0, or -4 plus 4z equals 0. Adding 4 to both sides, 4z equals 4. Dividing both sides by 4, I get z equals 1. So now I have my solution is x equals -3, y equals 2, z equals 1, or as an ordered triple in alphabetical order, I can write -3, 2, 1. Okay, let's look at another 3x3 system. So here, I'm going to first look at these first two equations together, and I am going to keep them the same. They're already set up to eliminate x's. So if I add them, my x's cancel out or are eliminated. And then if I add my y's, I get 3y. If I add my z's, I get -2z. Adding my constants, I get -7. And then I am going to take my second and third equation, and I am choosing to multiply my first equation by 3 and my second equation by 2 in order to eliminate my x's. And I had to eliminate the same variable that I did in the first two equations. So doing that, doing the multiplications, I will now get -6x plus 6y plus 3z equals -21. And my second equation results in 6x minus 8y minus 6z equals 14. Adding them together, my x's cancel out, and I end up with -2y minus 3z equals -7. So now these two resulting equations give me a system of two equations with two variables. So I'm going to put those two equations together, and I can choose elimination or substitution. Here I believe elimination will be simpler. I'm going to choose to multiply my first equation by 2 and my second equation by 3 in order to eliminate my y's, but I could have just as easily have eliminated my z's. So I end up with 6y minus 4z equals -14, and -6y minus 9z equals -21. Adding these together, my y's are eliminated, and I end up with negative 13z equals negative 35, or z equals 35/13. So I've got my value for one variable. I still have to find my values for x and y. Now I'm going to take this value of z and substitute it into this equation that we found in part 1 over here. And then I should be able to solve for y. And I could have just as easily have substituted it into the equation that resulted from step 2. So doing that, so I'm using the equation 3y minus 2z equals negative 7. And I had the value of z is 35/13, and I'm going to substitute it in. 3y minus 2 times 35/13 equals negative 7, or 3y minus 70/13 equals negative 7. So I'm going to convert my right-hand side so that it's over 13 and it becomes negative 91/13. I'm going to add 70/13 to both sides. 3y equals negative 21/13. Going to divide both sides by 3, and y equals negative 7/13. So now I know my z value and my y value. So now let's finish up and solve for x. So I'm going to take the equation here, go back over here for a moment. I'm going to take one of my equations with x in it so you can see where we came from. A quick way to go back to where I was. I'm going to take the equation from that last slide. That was 2x plus y minus 3z equals 0, and substitute in my values for y and z. So 2x plus negative 7/13 minus 3 times 35/13 equals 0, or 2x minus 7/13 minus 105/13 equals 0, or 2x minus 112/13 equals 0. I'm going to multiply everything by 13 to get rid of my fractions here. 26x minus 112 equals 0. Going to add 112 to both sides. So 26x equals 112. Divide both sides by 26. X equals 112/26. Or if I divide both my numerator and denominator by 2, that simplifies to 56/13. So that is my x value. So x is 56/13. Y is negative 7/13. Z is 35/13. And I can write that as an ordered triple as 56/13, comma, negative 7/13, comma, 35/13. Okay, let's look at a couple of word problems. So a store sells cashews for $5 per pound and peanuts for $1.50 per pound. The manager decides to mix 30 pounds of peanuts with some cashews and sell the mixture for $3 per pound. How many pounds of cashews should be mixed with the peanuts so that the mixture will produce the same revenue as selling the nuts separately? Now I'm going to solve these using tables like we did back in the first unit. But I'll point out where we could solve this using a system of equations instead of just writing one linear equation right away. So I'm going to create a table with columns price, amount, and cost. And I've got cashews, peanuts, and the mixture. Okay, so filling in what I know. I know that cashews sell for $5 a pound. I know that peanuts sell for $1.50 a pound. And the mixture will sell for $3 a pound. And I want to have a mix, but I'm going to have 30 pounds of peanuts in that mix. So I know that the amount of peanuts is 30 pounds. So I don't know how many pounds of cashews I will have. And so that will be my x, my unknown. And that means my mixture will have an amount of x plus 30, or 30 plus x. And this is where if you wanted to truly do it as a system of two equations, you could have made that y. but I'm choosing to make that x plus 30. So then for my total cost for cashews, I would do the price times the amount, 5 times x, 5x. For peanuts, 1.5 times 30. And for the mixture, I would have 3 times x plus 30. Or if I were writing a system of equations, I would have 3y. So now, remember from that first unit, we got our linear equation by using this third column. And I can write, to find the pounds of cashews, or to solve for my x, 5x plus 1.5 times 30 equals 3 times x plus 30. So we implicitly used substitution. We had taken our first, if we had used y, we would have been able to figure out that y equals x plus 30. And so we had kind of skipped a step back in Unit 1 in order to write just a linear equation right away. Okay, let's multiply out. We've got 5x plus 45 equals 3x plus 90. And subtract 3x from both sides. So 2x plus 45 equals 90. Subtract 45, 2x equals 45. Divide both sides by 2. We have x equals 22.5. And this is, x was representing the amount of pounds of cashews. So this is what I was looking for. So we need 22.5 pounds of cashews. We didn't need to solve for anything else there, just the x. Okay, so here's a second problem. We've got a restaurant manager wants to purchase 200 sets of dishes. One design costs $25 per set and another costs $45 per set. If she has only $7,400 to spend, how many sets of each design should she order? So I'm going to set up a table with columns price, number of sets, and the cost. So we've got design 1, design 2, and then a mixture or a combination of the designs. So we know she wants to purchase 200 sets of dishes. So we know that combined together, she will have 200 sets. And one design, or design 1, costs $25 per set. And design 2, or the second design, costs $45 per set. We don't know how many of each sets she should order. So, but we do know that she has $7,400 to spend. So that should be my total cost. One of my number of sets, I can make my x, and it doesn't matter whether I do that for set 1 or set 2. And so I know that I must have 200 minus x sets of design 2. But if I wanted to truly do this as a system of 2 equations, I could have made that y. And then I could have had an equation x plus y equals 200 and found that y equals 200 minus x. So I'm implicitly doing substitution here. Okay, to find my cost, I would multiply my price times the number of sets, so 25x, and 45 times 200 minus x, or with a system, I could have done 45y. Okay, I'm going to use that third column to set up my equation. 25x plus 45 times 200 minus x equals 7,400. I'll multiply 25x plus 9,000 minus 45x equals 7,400. On the next slide, I'll combine my x's. I'll get negative 20x plus 9,000 equals 7,400. I'll subtract 9,000 from both sides. Negative 20x equals negative 1,600. Divide both sides by negative 20. X equals 80. So I will, for step 1, or for the design 1, they'll need 80 sets. And for design 2, they'll need 200 minus 80, or 120 sets. So that is the solution to the second word problem.